Hello everyone and welcome back to my YouTube channel. Yesterday we have seen what is column, what is crippling load, what is buckling load, what is crushing load, what is strut. So in last lecture we defined all the things, and here we defined most important derivation for Euler's formula for column, Euler's formula for column, long column, and then we learn the different end conditions and effective length, or we can say equivalent length. Clear? After that we learn the ranking formula which is used for long column as well as short column. Based upon that, today we will see some of the numericals. Clear? So let's start today's session. Now first numerical I will read. A solid round bar of 3 meter long. So first I will write given data. Length is 3 meter, so I will consider in mm, and 5 centimeter diameter. So diameter is given 5 centimeter, that is 50 mm. Used as a strut with the following condition: determine crippling load. We need to evaluate the P. So value of Young's modulus is given 2 into 10 raised to 5 Newton per mm square. Now what is the formula to evaluate the crippling load or crushing load or collapsing load? That is P is equal to pi square EI divided by L square. So this L is nothing but it's a equivalent length. Now when both the ends of the strut is fixed, so first I will evaluate this first condition, that is both the ends of the strut is fixed. Then first we need to evaluate the effective length. So for that condition, effective length is L by 2. Now here length is 3 into 10 raised to 3 divided by 2, that is 1.5 into 10 raised to 3 mm. Now we can use the Euler's formula, that is pi square EI divided by LE square. So here pi square into E, that is Young's modulus, it is given 2 into 10 raised to 5 into I divided by L is given 1.5 into 10 raised to 3 whole square. Now here we have not evaluated the value of I, so I will evaluate I. Now here if you observe, structure or strut is a solid round bar. Clear? So here I can write for that pi by 64 into d raised to 4. Clear? Now here if you consider this I is nothing but moment of inertia having least count. Clear? So least value we required. So for that purpose, Ixx and Iyy we need to evaluate, and from these two, whatever the least values is there, that we need to consider. Clear? Now whenever we consider the least value, clear, then we need to identify along x-axis direction as well as along y direction, but for the circle we have same value, so I will consider the same. So pi by 64 into d is 50 whole square. So pi by 64 into 50 raised to 4, this will become 30 I equal to 306,796.1576 mm raised to 4. Clear? Just put this value over here in this equation, then this equation becomes pi square into 2 into 10 raised to 5 into 306,796 into 10 raised to 3 divided by 1.5 into 10 raised to 3 raised to square. So here the crippling load, sorry, this is the crippling load. So if you evaluate the crippling load, then it will be pi square into 2 into 10 raised to 5 into 306.796 into 10 raised to 3 divided by 1.5 into 10 raised to 3 bracket square. So it is 269,151.5691 Newton. So this is the value for crippling or collapsing load when both ends is fixed. Now second condition is one end is fixed and other end is hinged. So for that purpose I will evaluate effective length, that is equal to L by root 2. So 3 into 10 raised to 3 divided by root 2. 3 into 10 raised to 3 divided by root 2. So that is equal to 2121.323. Clear? So it is in mm. Again we will use the same formula, that is collapsing load or crushing load or crippling load or buckling load, that will be equal to pi square EI divided by L square. So here I will consider pi square, E value is 2 into 10 raised to 5 into I value is, here we have evaluated, that is 306.796 into 10 raised to 3 divided by 2121.31, sorry, 32 square. Then we get the crippling load. So here I will consider pi square into 2 into 10 raised to 5 into 306.796 into 10 raised to 3. Then here I must consider 2121.32 square. Now this value will be 134,575.82 Newton. So through this Euler's formula we can evaluate the crippling or collapsing load for the both different conditions. So in examination question will be remain same, only the conditions and conditions will be different. Depending upon that we must evaluate the effective length. That's it, and just put in this formula and we can get the crippling load. Now let's see the next numerical. A column of a timber having the section is given. So here if I draw the diagram, column of timber is given and the value is 15 centimeter. So instead of 15 I will say 150 mm and 20 centimeter, that is 200 mm. Clear? And the length is given, it is 6 meter, so 6000 mm. Both the ends is being fixed. Clear? So effective length will be L by 2, that is 3000 mm. Now here Young's modulus for timber is given, that is 17.5 into 10 raised to 3 Newton per mm square. Now they are asking about the crippling load. So as we have seen, so here I will consider the x direction, and here I will consider y direction. Simple. So first is crippling load they are asking. So crippling load, that will be equal to pi square EI divided by L square. Now E is known, L is also known, only I is unknown. Now I is nothing but it's a least value. Clear? So here I must consider Ixx. Now in previous case, if you observe, it was a circle, so Ixx is equal to Iyy, but here rectangle is there, so for that purpose I must consider separate Ixx and Iyy. So formula is BD cube divided by 12. So B is nothing but it's a parallel and D is nothing but it's a perpendicular side. Clear? So for Ixx, B is parallel value is 150 into D 200 cube divided by 12. So here I will get Ixx equal to 150 into 200 cube divided by 12. It will be 100 into 10 raised to 6. 100 into 10 raised to 6 mm raised to 4. Likewise, I must evaluate the Iyy. Same formula, BD cube divided by 12. So for Iyy, I will consider parallel value 200 into perpendicular 150 cube divided by 12. So Iyy, I will evaluate 200 into 150 raised to 3 divided by 12. So it will be near about 56.25 into 10 raised to 6 mm raised to 4. Clear? So from this it is clear that Iyy is less than Ixx value. Clear? So in this formula, what I will consider? I will consider the Iyy value. So here I will write pi square into E value is 17.5 into 10 raised to 3 into I value I will write 56.25 into 10 raised to 6 divided by LU value is 3000 square. So the crippling load will be pi square into 17.5 into 10 raised to 3 into 56.25 into 10 raised to 6 divided by 3000 square. Clear? So whatever you are taking bracket, it must be proper. So the crippling value will be 1.079 into 10 raised to 6 Newton. Clear? So this will be the crippling load. Now here second condition we need to evaluate, that is safe load for the column if factors of safety is 3. So always safe load, or we can say design load, is equal to the crippling load which you have evaluated divided by factor of safety. So whatever the value we have evaluated, that is 1.79 into 10 raised to 6 divided by factor of safety is given 3. So if I divide it by 3, then it will be near about 359.82 into 10 raised to 3 Newton. Clear? Or we can say it is 359.82 kilo Newton. So this is the safe load for that column. Simple. I hope numerical you have understood. Now these two were the simple numerical. Let's come to the next one. A simply supported beam of length is given 4000 mm is subjected to UDL. Now it is subjected to UDL is given, that is 30 kilonewton per meter. Clear? Now this is most important. We need to convert it into the Newton per mm. 30 into 10 raised to 3 divided by 10 raised to 3. So this will get cancelled. Then we get value for UDL equal to 30 Newton per mm. Clear? Now deflection is given. Now here deflection is given 15 mm at the center. Determine the crippling load when this beam is subjected to the following condition. Clear? What we required? We required to evaluate the crippling load, that is P, and that will be equal to pi square EI divided by LE square. Clear? Now here both the conditions are given, so from that condition we can evaluate the LE square. But what about EI? EI is not given in the problem statement. However, one of the thing is given, that is delta. Deflection at the center is given and simply supported beam is given. So here what they have given, simply supported beam like this, it is given having UDL. Clear? And the deflection at the center, so whatever the beam will deflect and the deflection at the center, this delta value is given. Now we must remember or the formula for deflection, otherwise we need to derive over here and then use. So I will use directly, that value is 5 by 384 into W into L raised to 4 divided by EI. Clear? So this value or formula we must recall from SFD and BMD chapter. Clear? If simply separated beam is there and deflection at the center, it is given by this formula. Clear? Now here I will put all the values. So here deflection is 15 equal to 5 divided by 384 into UDL, it is given 30 and length is 4000 raised to 4 divided by EI, and we want EI, just simply I will consider EI this side. Then if I divide by 15, then here it's very easy, 5 into 30 into 4000 raised to 4 divided by 384 into 15. So it is near about, just check it once because it is showing 6.66 into 10 raised to 12 Newton into mm square. Clear? I will just again recheck. Clear? So this value is clear. Okay. Now we know the EI value for this. Then first I will consider the first case. So what is given? Both ends are fixed. Sorry, first one end is fixed and other end is hinged. So for that purpose we must consider the case, that is one end is fixed and other end is hinged. So I will consider that LE equal to L by root 2, that is 4000 divided by root 2. So if I write 4000 divided by root 2, then it is 28.42 mm. So just put all the formula values in this formula. Pi square EI divided by LE square. So pi square into EI is 6.66 into 10 raised to 12 divided by 2828.42 whole square. Then the crippling load will be pi square into 6.66 into 10 raised to 12 divided by 2828.42 square. So this value will be equal to 8.21 into 10 raised to 6 Newton. Simple. So 8.21 into 10 raised to 6. So second condition is, what is given? Both ends is pin joint or hinge joint, then LE will be equal to L. So P is equal to pi square EI divided by LE square. So I will put all the values. 6.66 into 10 raised to 12, this is point, divided by 4000 square. So instead of just, I will put the value for L in same equation, then I will get 4.10 4.10 into 10 raised to 6 Newton. Clear? So this is the crippling values for the conditions when both ends are pin joint. Clear? So I hope this numerical you understood very well. Now next we will see using Euler's formula calculate the critical stresses. Now here we need to evaluate the critical stresses, not load, for the series of strut having the slenderness ratio, that is L by K. So L by K is 40, and in next we need to consider 80 under the following condition: when both ends are hinged and when both ends are fixed. The value of modulus of elasticity is given 2.05. So this will not be the value, that value must be 2.05 into 10 raised to 5 Newton per mm square. Remember these values. Clear? So modulus of elasticity for the material, obviously it will be into 10 raised to 5 Newton per mm square. Clear? Now here two slenderness ratio is given and two conditions are given. Now we will recall critical stress formula, that is pi square E divided by LE by K square. Clear? So this was the formula which we have evaluated for the critical stress. Simple. Now when both ends are hinged, then LE equal to L. Simple. LE will be equal to L. So I will consider L by K equal to 40. Then I will evaluate the critical stress. Critical stress, that will be equal to pi square E divided by LE by K square. So I will put pi square 2.05 into 10 raised to 5 divided by LE by K. It is given by 40 square. Clear? So if I evaluate pi square into 2.05 into 10 raised to 5 divided by 40 square, it is 1264.54 Newton per mm square. Clear? Now if slenderness ratio is 80, so I am using same formula. Clear? That is pi square into E divided by LE by K square. So here again we will consider pi square into 2.05 into 10 raised to 5 divided by 80 square. Simple. So just I'm changing the value of slenderness ratio. Clear? So this will be 1.6.13. Clear? So value Newton per mm square. Now I will consider the next case. What is the next case? Both ends are fixed. Both ends are fixed. So in that case, we know LE will be L by 2. Clear? Now critical stresses, then it will become critical stresses formula. It will become pi square E divided by, now here, L by 2 K square. Simple. Instead of L by K, here I will write L by 2. Now L by K is nothing but it's a slenderness ratio. So it is given 40. So pi square into E divided by 40. L by K is 40 divided by 2 square. So instead of slenderness ratio, we must consider the 20 value. So here we get the value of 5058.17 Newton per mm square. Now when slenderness ratio, when L by K is equal to how much? 80, then this formula will become pi square E divided by 80 by 2 whole square. So I think here we must consider 40. So it will be near about 1264.54 Newton per mm square. Simple. Now what was the change in first case and second case? So this was the first case. LV equal to L, and here LV equivalent length, that will be equal to L by 2. However, what is given? We given L by K, that is slenderness ratio is given. Clear? So 40 and 80. So we must consider this and we must evaluate the stresses. Clear? So this is not the formula for critical load, it is critical stress formula. Clear? Remember, these two are the different. So let's see the last numerical for the today's discussion. It is based on the Rankine formula as well as Euler's formula. Now here what is given? Length is given 1.5 into 10 to the 3 mm. 1.5 long column having cross-sectional diameter. Now cross-sectional having diameter. So diameter is equal to 50 mm. One of the end of column is fixed in the direction and position, and other end is free. Clear? So definitely LE is equal to 2L. Taking the factor of safety 3. Factor of safety is 3. Calculate the safe load. Safe load we need to evaluate. So for that purpose we required crippling or critical load or crippling load. Crippling load we need to evaluate. Clear? So first we will use the Rankine formula. So crushing stress is given, that is sigma c is given 550 Newton per mm square, and Rankine constant alpha is given 1 upon 16,000 for pin end. Clear? Now for Euler's formula, Young's modulus E is given for cast iron, that is 1.2 into 10 to the 5 Newton per mm square. You must evaluate the I. Clear? Now first we will see the I, as this is a circular. So Ix, that will be equal to Iyy, that will be equal to I. So pi by 16 into d raised to 4. So pi by 64 into, sorry, here pi by 16 is not that, pi by 64, and what is the value for d? It is 50 raised to 4. So here I will consider pi into 50 raised to 4 divided by 64. So its value is 306.796 into 10 raised to 3 mm raised to 4. So as both the Ix and Iyy is same, so I will consider this least value. Clear? In both the formula. So I will write rankings formula that is equal to P equal to sigma C into A divided by 1 plus alpha into LE by K square. Simple. Now here we have not evaluated the K. Clear? So for that purpose I know this I. What is I? AK square. Now we know area pi by 4 d square. Clear? So first I will evaluate pi by 4 d square. If you put the value pi by 4 50 square, then pi area will be equal to 1.9634 into 10 raised to 3 mm square. So if you put this value, if you put this area value over here, then K will equal to under root of I by A. So I will evaluate I value, that is 306.796 into 10 raised to 3 divided by answer. And if I take root over of K value, so it is 12.5. Now K is known, I is known, sigma C is known, area is known. Just put all this value. So sigma C value, crushing stress is given 560. So 560 into area is given 1.9634 into 10 raised to 3. 1 plus alpha value, it is also given 1 divided by 1600 into LE, it is given 3000. Yes, am I right? 1.5 and LE. So here I will evaluate 2 into 1.5 is equal to 3 meter. So that will be equal to 3000 mm. Clear? So here I will consider 3000 divided by K, we evaluated just right now 5 whole square. If you will calculate, then the critical load with the help of Rankine formula, it will be equal to 9902.7 Newton. Clear? Sorry, it is not that much. It will be equal to 29708.1 Newton. Clear? Now here we require to evaluate the safe load, and that will be the factor of safety. So 29708.1 Newton divided by factor of safety is 3. Clear? So that will be 9902.7 Newton. So this is a safe load which we have evaluated through the Rankine's formula. Now I will use the Euler's formula. So we already know that is pi square EI divided by LE square. So you just need to put all the values as we know all the value. So pi square E is given 1.2 into 10 raised to 5 into I value which we have evaluated, that is 306.79. 306.79 into 10 raised to 10 raised to 3, and we know the LE, that is 3000 square. If you evaluate the load, from the Euler's formula. So this will be equal to 40200 Newton. And if I want to evaluate the safe load by Euler's formula, that is equal to crippling load divided by factor of safety, it is 3. Now if you just do the calculation, it will be equal to 3401340. Okay, so if I compare the safe load 1340 Newton, clear, then you might thinking that this is the load which we have evaluated from the Euler's formula, clear, and safe load through Rankine formula which we have evaluated 9902 9902.7 Newton, clear. Now if you observe the same numericals, if you observe, then it is showing that at this load only, this is through Rankine's formula, clear. So from these two I am concluding that if you observe for long column, Euler's formula is very good. As you observe at this amount, just at this 1340 Newton, this entire column or strut, it is going to fail, clear. Now this will not sustain this much of load which is derived from the Rankine's formula, clear. So we can say that if long column is there, for that purpose we must use the Euler's formula only, clear. For both, for long as well as short column, we use the Rankine formula. However, we will get good result through the Euler's formula only. Thank you. If you like this video, then you can subscribe the channel. I hope you understand the all numericals which we have saw today, and if you have not seen the last video, then please see this video which include the all information regarding the what is column, what is stud, then how the failure will takes place, what are the stresses, what are the assumptions, then sign convection, then we evaluate how we evaluate the formula for the crippling load, then we learn the effective or equivalent length for column when both ends are hinged, one end is fixed, one end is free, both ends are fixed, one end is fixed and other is hinged. For that purpose we evaluated the different effective length, and then we learned the critical stress, what is the slenderness ratio, and then we evaluated the Rankine's formula which is used for the long column as well as for short column. I hope you understand the concept of column and strut, clear. If you like this video, then you can subscribe the channel. Thank you. Don't forget to subscribe the channel.